Okay. My presentation is about our finite element library, our HP adaptive finite element library. But let me start with some introduction of our group, of what we do, etc. So we have a name, HP Group, which explains what we do, and we are actually based at 3 institutions: University of Nevada in Reno, which is where Pavel is, University of West Bohemia in Pilsen, which is where most of us are from, and Institute of Thermomechanics in Prague. These two are in the Czech Republic. What we do is described here, but we are concerned with general purpose HP adaptive software for engineers, for scientists, for us as well. We do have 3 kind of products. Hermes2D is the library I'm going to talk about in some detail. It's an HP FEM and HPDG C++ based library. Then Agros2D, which is the graphical engineering kind of tool with massive pre and post processor, was presented yesterday with all the functionality it has. And we do have legacy 3D code, HP adaptive 3D code, but it does not reach the amount of features we have in 2D now. And it's our plan to maybe have it running in API and everything in a couple of years. Okay, press a button here. So something about our team is down here. So these are our faces. Some of them you could see at this conference. The first 5 actually. Some of them over there, but over here, etc. And that's it. And I will just go to the library itself, because also the engineering tool uses the library as its underlying mathematical kind of solver, etc. So this is a web page where you can find anything you are looking for, including the mailing list, email address. If you have any more questions, you don't find here. But we'll just quickly skip through some documentation we have. So we do have all kinds of documentation. We have a Doxygen documentation. I will be showing that quite a lot because it's actually well organized, I hope for you. Then we have all sorts of tutorial examples, guides, and this PDF that goes through installation, first steps, how to get it running on Linux, Windows, Mac, etc. And potential collaboration via GitHub, because we have open GitHub repositories. Okay, Doxygen documentation is, I would say, the primary source of information for anybody who would like to use Hermes to solve a PDE problem. So you could find, I hope, anything, and if you don't, just use the mailing list address. As I promised, this will be a very short presentation, and it'll be mainly hands-on, so I'll be showing the code itself. So this is just to show you that I would say that it's easily searchable for particular information one needs. But now I will go to the example that I called Quick Show, which will be to present how easy it is from the mathematical setup to build up a solution using nonlinear solvers, using spatial adaptivity, using time-dependent problems, etc. So it's sort of a cookbook, and the idea is to show that it is really following the math closely and it's not difficult. I hope it will be the case. So first thing that can be written in a couple of lines is, and I'll sit down, excuse me, is some heat transfer equation. Well, and if one just wants to have some steady state solution, so basically solve a Laplace equation or Poisson equation, what one has to do in math. So one has to have a mesh, one has to have a weak formulation and boundary conditions. And that's actually all one needs for Hermes to calculate the solution. So I have to have a mesh. This is just a technical thing. I have to have my boundary conditions. So let's say it's zero somewhere. I will show you the domain. But this is how easy it is to set boundary condition. This is just a marker that represents a part of the boundary. Initial condition is just a class with common interface where all it has to do is to return a value based on the reference or the real coordinates in this case. And then some either linear or nonlinear coefficients in the equation, and then the weak formulation, which is also rather easy. It looks just like this. This is a switch from me just to have this presentation slightly running or smoothly running. So matrix form and vector form, and these together are all the lines that one really needs to provide. Then one instantiates a solver. In this case, it's a linear solver. Calls solve. It does everything for the user, and then one just gets a solution and displays it, just like this. So the domain looks like this. The zero boundary condition is here, and the non-zero kind of condition is here. This is the mesh. Yeah, it's not very easy to see, but it's a rather coarse mesh. So what would be the next step in the process of getting some valuable solutions? Because this is not valuable. This is just some academic high school example. So first thing, how difficult is it to raise polynomial degree? So it goes like this. I would just change this number, which is actually passed to the space creation, and I do have it's building now, but I do have a higher order polynomial degree everywhere on the mesh. Well, this is still a rather coarse mesh, so my next step would be to uniformly refine the mesh again, and it's again rather easy. So it looks like this, but this is a linear case with a really simple mesh. So let's I'll just change numbers. Let's try a nonlinear problem, and again I'll be showing how easy it is to switch from linear to nonlinear. Well, I prepared some stuff, so I can just undefine this.
Increase both sides.
Oh yeah, thank you.
Yeah,
Thank you.
now there is some readability.
Oh, sorry about that. Yeah, I can see it right here. So I will just switch the linear to nonlinear, but I want to be pointing out all the way through the presentation that it really follows the math. So if we switch from linear to nonlinear in math, what we have to do is to just change the equation, use the nonlinear solver instead of linear, and change the weak formulation if we are using the Newton's method, because we need to switch from matrix right-hand side to Jacobian residual. And these are actually all the points that need to be done in Hermes, nothing else. So if you take a look what this changed, so it changed the linearity from the linear parameter to nonlinear one. And this nonlinear one is just 1 plus the solution to the power of the past argument, which is 4 in this case. The next thing it changed from linear solver to nonlinear solver, the Newton solver, which have the identical interface. So there's nothing more changing in the code. And the last thing it changed the formulation from this one, from the matrix and vector form to Jacobian or residual form. Sorry. You need to keep reminding me. Thank you. And well, let's try if it calculates. And I didn't change anything else, so the idea is really the rapid prototyping. And this is actually an intentional crash, because what does Newton's method do if it just starts from a zero initial guess? Well, it may not converge, right? So we should give the Newton's method initial condition in this case. And since I'll be showing also a time-dependent problem on this code, I already have an initial condition prepared right here. So why don't I just try to plug it in, like solve from the initial condition. And we'll see. Okay, so yeah, it calculates. So it was really easy to make it running following just the math. But one of the nice features about Hermes is that it can use curved elements. So let's make this a little bit curved, the domain.
Lucas, is this a hybrid mesh of rectangles and triangles, or
Yeah.
visualization?
It's a hybrid mesh, yeah. Well, we allow for hybrid meshes, and in fact you can also define your own element. There's a common kind of interface you can do with. So how do I achieve the curvature of the domain? So either I can use some mesh generation tool or some engineering stuff, or I can just retype several lines in our code, because we allow for super coarse meshes, because our adaptivity mechanism can take care of that. So this is actually just the description of the mesh, with some variables, vertices, elements, and edges. And optionally, it can also have some curves. So I can just uncomment this in the XML source file for the mesh.
Because the font, yeah.
Yeah, but is it? Yeah, okay. So this was pre-commented before, and I just uncommented it, so that now it's going to be read right here by the program. I just change the file, and it will contain the curved elements. But again, the Newton method, it is also intentional. The Newton's method didn't converge now because the boundary condition was a bit more difficult to handle. So what can I do with my Newton solver? Again, we use all kinds of settings for our Newton solver. Damping, we use conditional reusage of the Jacobian for time saving, etc. And I will just quickly show you how easy it is to make the Newton converge, even though the Newton out of the book would not, because it just cannot handle the nonlinearity. So I'll just write solver and set some manual damping coefficient down to 0.5. And I would say that the max L iteration would be 20. Okay, it's 10 by default. There are always defaults, and there are always comments, and it's documented, so one can always find what the defaults are. And of course, I tried this before, so I hope it will converge now.
Remember, it's really
Yeah, I hope. Yeah, it does. Yeah. Now it has the curved boundary, it converges, and if I don't know how to really increase this font size, but the output says that it's reusing the Jacobian. It also kind of handles the damping factor, etc. So this is the solution I obtained, and one can see that it's not perfect. Right? It's actually far from being perfect. So there is this boundary layer that is not very well resolved, and that's where the spatial adaptivity would come into play. But since I do have to follow certain procedure, because otherwise my comments and uncomments will just ruin everything, I will first show the time-dependent problem. So then I will go to spatial adaptivity. Okay, so this region I will comment out because it was the stationary problem. And I will show you the time-stepping loop. And we can see that, we will see in a second, that if we don't use the spatial adaptivity for now, so I will comment this out. Right, so now this is the way I want it to be. So if I don't use spatial adaptivity and I just added the time stepping to the equation, what I have to do in math, so, I mean, I changed from stationary problem to time-dependent one. So I have to change my equations, right? Because, well, there is this term coming from the integration of time integration, and I have to do some time looping. And I will show you that this is exactly what we added in Hermes. So there's again nothing else. So if we take a look at this, it does this block while current time is smaller than some final time. But it's exactly the same as it was before for the stationary problem. So you just solve, get a solution, and display it. And what is there new is the copying from the new solution to the previous one for the next run, and also increase the time and time step number. But I also have to change the equations, and so I'm basically changing the weak formulations. So I go to wherever it was where I set up my weak formulation. I can use just this weak formulation, and I will comment out the steady state one, or the stationary one, it's probably just a bad name, and I will use the weak form that is time dependent. And since I only wanted to add some forms and not to write a new form from scratch, I did that. So the time-dependent weak form actually derives from the stationary one, and it will just add the matrix form for the time derivative form and the vector form. I mean residual and vector form, because we are now using Newton. So that's all I did, and let's see if it works. Okay, so now I have a time-dependent problem, which is same as before. The nonlinearity is the same. I'm using implicit Euler in this case. One can just play around with the weak formulation, or one can use our sort of a library of time integration methods. But yeah, this is the freedom. One can use whatever he wants, and we provide some default or some predefined things. So I'm using my own because it's very simple now. But still, the solution is rather ugly. So let's plug in the spatial adaptivity, and you can see. I will just stop this because otherwise it will just continue until the final time is reached. And so in this case, I can already delete this region because we won't be using it. And let's take a look at what the spatial adaptivity does. It's actually kind of large, right? It's probably the largest piece of code that is in there. And what it does, so for each time step, it would, I mean, if somebody happened to be at my slightly chaotic presentation of adaptivity some days ago.
Lukas, do you want to?
Yeah, sorry. But yeah, I wanted to show how large it is. Now you saw it, so okay. So it would just have a loop where it would be looking for a solution good enough by starting with some reference solution, calculating, measuring the error, adapting if necessary, doing this loop until the error condition is fulfilled. So this is exactly what is in the code. So it constructs globally refined reference mesh and space. It solves, and then under it will project from the reference solution to the coarse component to obtain the coarse component. It would calculate the element error. And at this point, I would like to say that there is a class for it. It's called the error calculator class. And there is a whole bunch of default error calculators available. with all kinds of norms, but one can easily just take the base class, which provides the interface, and just rewrite one method. It will calculate the error. 3 lines of code, and one can experiment around with all kinds of error measurements based on anything that's in the code, really. And, so this is what we mean by rapid prototyping. One can just play around and change only tens of lines of code at most. It also uses some stopping criterion that was also in my kind of presentation, and etc. But right now we are here, so it calculates errors, it prints out the error estimate, visualizes the solution, and if the error estimate is smaller than some error stopping criterion, it would stop, otherwise it would adapt. Okay, let's take a look how it performs in practice. Yeah, I might have actually taken down some refinements and plan to degree, because the adaptivity will take care of this. So I don't have to a priori say that my mesh should be improved in any way. And you can see the automatic HP adaptivity taking care of the solution. Right? So it found the region where it was necessary to refine, and it continued to do so until the error was met, and then it would just go on to the next step, etc., etc. There is no coarsening in this example, although it is, of course, a feature of Hermes as well. And let's take a look at this. So, yeah, how it looks kind of like what we would expect. Okay. And yeah, it would just go on refining the mesh if necessary, continuing with the next time step if not, all the way to the bottom. Okay. So that is it with this example, and now I'll be just showing basically some kinds of more advanced, let's say, examples, just to have some idea how far can one go with this general code. So this first thing is linear elasticity code using HP adaptivity. So it's a beam that has some cracks in it, and it's loaded with its own weight, and it uses what we call the multi-mesh approach, which in this case is not as good performing, as well performing, because the two solution components, the X and Y displacement, are qualitatively sort of similar. But we can see that each of them has the mesh adapted as it needs, and this is the von Mises stress calculated with the displacement visualized by actual displacement of the domain. So and again, we can take a look at the code, but I think it's unnecessarily boring. So the next step, I think I will just show 2 examples or 3, is that we can really do HPDG out of the box. So there is no special code for it. And this is a GAN channel problem with all kinds of shock capturing options. And if one takes a look at the blocks of code, it follows the math, really. So all it does is that it would load the mesh from some file, initialize solutions, set initial conditions, set some filters for visualization, because of course we are not always interested in this quantity in the solution itself. You can be interested in the function of more solutions, and as in the case of Mach number. Then we would initialize the weak formulation problem. We would use in a linear solver, because this is actually explicit time skipping used, and you just run the loop. So let's take a look if it Whereas, of course, this is on a rather coarse mesh, so that it actually evolves kind of in front of the audience. But this is just to really show you that this is not difficult to do as well. And I will just show you a quick video. So in the end, it would look just like this. It's the HPDG automatic refinement used for capturing the shock wave. Okay, so it goes like this. And yeah, and it reached a steady state. But that's the reason why we did it, and that's it. We can. This example was without adaptivity. With adaptivity, it's of course a little bit more challenging to write the code, but I will not go there. This is a nice example also of what the rapid prototyping is really for. This is a waveguide example. So this is a waveguide. I mean, I'm not the engineer, those guys are over there, but I was told that this is used for antennas where the signal has to travel in some fashion, and some aspects of the signal are supposed to be eliminated by some kind of thinner part. And of course, the threshold has to be found. It's not, it's not obvious what the threshold in terms of frequency will be. So one can calculate it, for example, using finite elements. And I wrote a simple program that would just calculate it and ask me if it's okay, if the wave travels through. I would say again it does not. So how do I want to change the frequency? The frequency right now is 16 gigahertz. So let's say I will change it by -3 gigahertz. Okay, so it was not a good decision. So let's increase it by 4. Oh yeah, now it travels through. But it's rather strange that the wave has actually the biggest amplitude after the thin section. So I can play around with this, and I mean, I happen to know the solution, so it's rather easy for me to do this. But you can get the idea. And writing this example is again maybe 200 lines of code. So if an engineer comes to this or asks some programmer to come sit by him and write this, it's rather easy. That's what we are trying to achieve with the software. I can show you very quickly. So these are all the variables that are. I don't think I can really increase the font size here, but well, this is the list of variables in the example. It's like 20 variables, and most of them are frequency, epsilon, beta, omega, so the physical things. It's not like a bunch of technical selections of whatever the library needs to run. So it's the rapid prototyping we have in mind. So I will just end it here because I think it's enough said. And the last thing I would maybe say is that we are always open to collaboration in any sense, by engineers, by other programmers, by developers of our competitors, etc. Okay, thank you.